My name is Professor Newell Washburn. I'm in the Departments of Chemistry, Biomedical Engineering, and Material Science and Engineering at Carnegie Mellon University. I'll be talking about embedding domain knowledge for machine learning of complex material systems. Complex material systems are ubiquitous. They are all around us in the form of surfactants, coatings, various consumer products, electronics, agriculture, pharmaceuticals, and other things. The design and optimization of these generally involves working in a high dimensional space due to the number of experimental variables that we have at our disposal. But the way we currently approach this design process is largely based on either intuition or really what are incremental changes to existing products. So there's a real need for design tools to do this process. So we're going to be talking a fair bit about response surfaces in materials design, and a response surface is really just a representation of, as given experimental or input parameters change, so these would be your X variables, how do the system properties or responses change? And so as I said, in materials design, we commonly work in high dimensional space, which just means we have a lot of variables at our disposal. And relative to this high dimensionality, the experimental data sets that we commonly generate, with a few exceptions, they tend to be sparse. And so the general problem in response surface methodologies is if you're given some data points, which in this plot are shown as green circles, we want to know what the space in between these points looks like. So in this example shown here, and this is taken from our recent paper in the special issue of MRS Communications, we show the 4 points linked by a fairly simple parabolic surface shown in red, or a much more complex hypersurface shown in blue. And the question is, if you only know these 4 points, how do you know what's in between? So one task in machine learning is determining what these response surfaces look like, really connecting the input X with the output Y. But oftentimes in traditional machine learning, this process is just based on statistical inference, which has the downside that it requires big data in order to accomplish this. And then the second issue is really around the interpretability of these models. So if you are able to work out, if you have an algorithm that can work out what this response surface looks like, can the human understand what it means? So the general problem in machine learning is represented here in this figure to the right, and really it's you've got input features we call our X value, and these are shown as the blue circles in the bottom, and our output is shown as the Y on the top, which is a green circle, and then in between, that's where most common algorithms will do what we call statistical inference, basically just looking for patterns in the data that will connect input and output. But again, the problem with these is that for most machine learning algorithms, it requires a lot of data, a lot of examples of this in order to really train the algorithm accurately on what these connections should be. And so in this work, we've really discussed 4 different examples of how we can embed domain knowledge into these algorithms. And the advantage that this has is a few things. One is that it should reduce our data requirements. And then the other is that it should make the models more interpretable to humans. So specifically, we talked about 4 different examples, 4 different basic approaches. One is embedding physical chemical properties. And this is basically just, in the example shown to the right, we have the red circles are supposed to be some sort of bridge between the input and the output. And so you could calculate descriptors. So this could be an example of this would be using quantum chemistry to calculate certain properties of the system that contribute to the ultimate property that you're trying to predict the output. Another example would be embedding similarity, and what that means is really just saying if you have a library of examples, you can start to say, well, these should look similar to each other, and then you can start to cluster another group together. Conversely, you can embed what you know about the system properties, and that's focusing at the top of the algorithm, this green circle. And really what you're there what you're doing there is you're basically putting down rules that will relate different observed quantities. So this could be, for example, using symmetry arguments to make estimates for how different responses should look depending on how you change the output. What I'm going to talk more about today is actually embedding physical equations. And in general, with a traditional machine learning algorithm like a neural network, statistical inference that's shown on the bottom with this, what we call H is our hidden variable, shown here, or hidden layer. What we have shown in our work is that we can actually embed, rather than having essentially nodes that really don't know what they're looking at, we've shown that you can actually embed domain knowledge and use this as a bridge to go from input to output very efficiently. So the example of the algorithm that we developed is shown here. It's called, we would call it hierarchical machine learning. And really, you could think about it as like three layers. At the bottom is, what is it? So these are our system variables, our input variables, our X's. At the top, we've got our system responses. What does it do? But in the middle, really, this is where we embed, we called it in this work single physics interaction, but really is answering the question, how does it work? So I'll motivate this with an example. It's a work that we published recently in predicting the mechanical properties of polyurethanes. In polyurethanes are a diverse class of polymer that are based on combining an isocyanate, which is examples are shown up here, with a polyol, and these are their examples shown down here. You can vary the ratio at which you blend these two, and then you have a lot of different chemistries as far as what is actually in between these functional groups. That's the monomer chemistry. And so we wanted to develop a model where we could predict the mechanical properties using hierarchical machine learning. So in HML, we have to answer the question, how does this work? How does this property work? And in the case of microstructure, in the case of polyurethane mechanical properties, they're really driven by the microstructure. So there are three main contributions to this. One is the tendency of these polymers to microphase separate into a hard segment domain, which is shown as these gray plates, separated by the soft segment domains, which are shown as red lines. Another force is the intermolecular hydrogen bonding that exists between chains. And then finally, you've got this variable of the polymer molecular weight and architecture, which can depend greatly on whether you're using bifunctional or trifunctional monomers. And we have examples of both in this work. So the challenge in this approach is then to represent what we call this middle layer, these hidden features in terms of things that you can actually go in and measure. And so while it can be challenging to directly measure the extent to which hard segment domains have formed, we can get an estimate for that just by counting functional groups. So for example, we know that these benzene type rings will tend to aggregate and form hard segment domains. For estimating the physical crosslinks due to hydrogen bonding, we used data from infrared spectroscopy, which are shown here, and using shifts in some of the absorbances of carbonyl and amide bonds. And then finally, we estimated the molecular weight and architecture of these polymer chains by doing Monte Carlo simulations of step growth polymerization. And an example of what the resulting chain looks like is shown there. So the algorithm for predicting the mechanical properties of polyurethanes is shown here. Our input variables, again, are which monomers did we choose, what was the ratio of isocyanate to alcohols. The responses that we were looking at were ultimate tensile strength, ultimate elongation, and the tan delta, which is the tendency to display either elastic or viscous mechanical responses. And then the bridge that we used in developing this model were the infrared spectral data, which told us about, told us about hydrogen bonding, the tendency to form these hard segment domains, which is given just by counting functional groups, and then finally the simulations via Monte Carlo that gave us an indication of the molecular weight and chain architecture. So our training set was much smaller than you would do for some classic machine learning problem like text recognition. We only had 18 samples in there, but they were taken from a mix of 3 different isocyanates, 3 different polyols at 3 different indices. And so 18 really only represents a small subset of the total possible number of permutations you could have. But we felt it would be a good test for the algorithm to see if it could start making good predictions. In machine learning, you generally want to look for trends in your data that may be lurking already. And so here, what I show is just a plot of our different outputs. So this scatter plot up here is the ultimate elongation, the correlation between ultimate elongation and the ultimate tensile strength. And what we see is that there really isn't a very strong correlation. So knowing the ultimate tensile strength really doesn't tell you much about what the ultimate elongation should be. But it's a good idea to go through your data and look for these kind of hidden correlations. There are many tools in machine learning that can be used to build these kind of predictive models. And in our algorithm, it's really, in a way, an algorithm of algorithms. And so we used a tool called a random forest in one of the steps to relate how the mechanical properties depend on what we call our middle layer variables. And the nice thing about that is that in random forest approaches, you actually can generate a sort of hierarchical list of the features that were most important in determining a response, at least based on your data. And so what we see here is that, for example, the stress value at the break was actually most strongly correlated with changes in both in the infrared spectra, which we associated with the intermolecular hydrogen bonding. And that was interesting because it really suggested that the last bond that was holding these materials together before they broke were in fact these hydrogen bonds, which is physically reasonable. We can also do tests of, well, do you have to go to this trouble of doing these other measurements to populate a middle layer? So if you take a classic machine learning approach and you look at how the correlations change for relating the mechanical properties that you measure to the input variables, that would be a classic black box model. And what we see below is that especially for the test score, which is the more relevant score, that prediction is really at best 30% accurate in explaining the data. Versus when you include this middle layer variable here, what you find is that you have a greater than 90% accuracy in making predictions on the data, which suggests that embedding this domain knowledge really significantly improves the accuracy of the predictions. In our group, we've done other work. We recently published a study on 3D printing of silicone. That was interesting in part just because it showed that we could look at the coupling between many different classes of variables. So in that work, we had material variables in terms of which silicone ink we were using. We had formulation variables in terms of how things were mixed. And then finally, we had process variables, which was actually the settings in the 3D printer that were used to make this material. But we've also done modeling of direct metal paint, and then plasticization of cement paste, really showing the diversity with which you can do these types of machine learning models in material systems. So in conclusion, embedding domain knowledge in machine learning algorithms is really a powerful and effective tool for improving the models that are built. What we really think is that the middle layer is reducing the complexity of the hypothesis space that we have to search through in trying to determine what this response surface looks like. And it makes the algorithms much, much more efficient at essentially building a reasonable model to explain your data. We're still exploring the role of causality in this, and then sort of asking questions about what are the underlying biases that we've embedded into these models. But we think it's a very promising approach for data-driven tools in materials research. One of the real highlights of it is the really very manageable size of the data sets. Again, in this work, we only made 18 different samples. We did some additional surrogate measurements, such as infrared spectroscopy, but it really was not a classic big data type approach. And the other thing that we think is interesting about this is it opens up the possibility of really trying to capture deep technological expertise or deep scientific expertise in algorithm form, really taking the domain knowledge and making that an integral part of the algorithm.
Thank you, Dr. Washburn, for the fascinating talk. And I'm also pleased to say that Dr. Washburn is here to answer your questions. So I'll start with a question that draws a comparison to some of the talks we heard earlier, which is some folks are interested in knowing about if these techniques can apply to organic materials, which has been answered, but I think I'd like to amend that a little bit and ask, so, compared to the organic materials we heard a lot about in the previous talks, what would you say that the biggest contrast is with the organic materials that you studied here?
I think there are a couple things. One is the, the smallness of the data sets. Some of these systems, especially, complex colloidal systems, it's very difficult to get, a large sample size on. The organic systems can have maybe different sensitivities to processing conditions. So that was, a subject that came up earlier, and certainly I think that's, accentuated here. And then finally, I think there are, can be a number of hidden variables that in organic systems, and part of it is just the complexity of their composition, and then also just the long equilibration times that can be that can surprise you. And so, I think there are some subtleties in working with these as opposed to some other material systems.
Thank you. Okay, so moving on to some of the newer questions. So, you introduced this really interesting hierarchical strategy for learning properties and to performance and the composition. And so we had a question coming from the University at Buffalo about how do you represent uncertainty inside the physics-based layer at all, if at all? Is the assumption there that it is fixed in the known physics, the physics known for the system, or are there unknown parameters in these physics-based models?
Well, at least in the early incarnations of it, what we were doing was we were really making a maximum likelihood estimate for how the system variables, the variables that were living in the bottom layer of the model would influence what was going on in the middle, which was what we said was where the physics was. What we're doing currently, and we have some papers that are just about to head out the door on this, is sort of estimating the prior distributions in a Bayesian context, estimating the prior distributions, which is basically you could get at from just repeating the same experiment over and over again, just to see what the underlying variance of or intrinsic variance of the system is, and then you can mathematically model that with a Laplacian prior. So you can do similar kind of regression type approaches where you're using these Laplacian priors to as a way of embedding the underlying distribution, and then because you're carrying a full distribution from the middle up to the top, you get this sort of propagation of uncertainty, which I think can, as long as it doesn't sort of blow up on you, can give you sort of meaningful estimates for the uncertainty in the overall materials or system properties.
Great, thank you. So the next question is coming to us from Sandia, and it's really related to scalability to new materials, which is that if you wanted to expand to a larger type of precursors or larger range of precursors, would you be required to obtain the intermediate layers, for example, the IR spectra, for each new combination?
No, that's a great question. Ultimately, we're still sort of exploring that question right now. But ultimately, what we would like is really kind of a system where we do all this sort of front end work on embedding the underlying chemistry, physics, and engineering in these systems to when we're training the algorithm, but then we can basically seal it back up into a black box where once you've kind of established all the connections, then you really are just inputting, the basic information about, what your input variables are. So it would be, I think what the question was getting at, if you had sort of a new set of monomers, in this case, for our formulations, could you just say, well, this is what they look like, this is, their molecular structure, and then run it through the black box and get meaningful predictions. And that's something that it's a great challenge, and we're working toward.
Great, thank you. So another question that I think is you've showed a lot of interesting, discoveries from both the learning side and also the materials side. And I think, I was hoping you can speak for a second about how a materials researcher finds the right collaborators, or is this something that, how did you get started in this process, and what resources did you need? Was it collaborations? What did you have to learn? Just elaborate on that process a little bit.
Sure. I mean, we started in this area about 5 years ago, and it was really more that, I had this long-standing interest in how do we design materials for function, and I only kind of backed into machine learning because we'd run out of other options. I mean, I'm lucky to be at Carnegie Mellon, which has the world's first sort of standalone department of machine learning, and so I have a terrific collaborator through the machine learning department. But I mean, I think increasingly, at least for getting started, there are a lot of tools as far as through MATLAB or Python that will really let people, and even when we're working in systems, we will just take out-of-the-box solutions and just run it through a black box just to kind of start to get a sense for, our data holding together, are we getting kind of coherent predictions even based on these small data sets before we sort of dive into, embedding physical knowledge of these systems. And so I think there's certainly, it's less of I think there's less of an activation barrier to at least, starting to explore data-driven approaches. And really, I guess in the paper that we published in MRS Communications, we really tried to make a case that there's this sort of kind of phase space or parameter space where you've got, kind of the extent of your domain knowledge, ranging from basically none to sort of perfect knowledge of deterministic physical laws. And then also on an orthogonal axis, the amount of data ranging from, essentially none to, essentially infinite. And that, will be a lot of these hybrid approaches are coming online right now. And they're going to let us start to really, I think, ask some interesting questions and learn more about these systems, design systems, and do things that really weren't possible before. Where we were just sort of isolating either we're only using physics-based models or we're only using sort of machine learning, out-of-the-box machine learning approaches.
Excellent. So a final question to you comes from a graduate of your university, which I understand is called CMU, and is that are the middle and the bottom really different? They're all descriptions of material in some way that is human convenient for description. Molecular structure are measures of other things that are results of molecular structure. You try training a machine learning process with only the middle layer and not the bottom layer.
Sure. I mean, we actually have, in my group, we actually have, sort of discussions about is this a bottom layer variable or middle layer variable? I mean, what we think about is the bottom layer is really anything you could go into the lab and control. And so that would be like which monomer you pick, what temperature you process the material at, things like that. The middle layer is actually, I mean, in some ways, we should have just called this prosaic machine learning because, really what we're doing is we're taking a very literal interpretation of, the hidden layers in kind of a Bayesian framework or a neural network and just saying, they may be hidden in terms of, they're latent variables that are ultimately what's controlling the system responses, but we have kind of either, experimental or computational ways of getting kind of like a proxy measurement of those. And so they are, I think actually distinct, when formulated, rigorously. I think the middle layer is really things that, you can't necessarily go in and pick, if the TG of your system matters for the ultimate response. You'd have a hard time going shopping for something that had a particular TG, but you can shop for something that has different composition and hope to influence the TG, which will then hope will influence the overall system property. So I think from a kind of, more classical statistics approach, rather than calling it a hidden layer, or rather than calling it a middle layer, if you think about it as a hidden layer, and then, can we try and lift the veil on that? That's really the underlying theme of our approach.
Fantastic, and you've convinced me, so thank you. And thank you very much, Dr. Washburn, for the wonderful talk and questions. Our final talk